In our very first lessons on approximating the area under a curve, we looked at the curve y equals 4 minus x squared over the interval 0 to 2. And we approximated that area in many different ways. With n equal 4, with just 4 rectangles, we found a lower sum, and the approximation was 4.25. We found an upper sum and approximated the area to be 6.25. So we took that to mean that the true area has to be between these two things. Also with n equal 4, we found a midpoint rule approximation and found it to be 5.375. And I told you that this was really close to the exact area. Well, in this video, I actually want to find that exact area. And we're going to use the same method proposed in the last video, where we first write down a Riemann sum using subintervals of an equal width and right-hand endpoints. We then work with that Riemann sum until we have a formula just with n on it, and then we take a limit as n approaches infinity. So, to start, I need to think about a Riemann sum. So the sum from k equals 1 to n of f of ck times delta x. Well, my delta x, b minus a all over n, is going to be 2 over n, and my right-handed endpoints, a plus k times delta x. So 2k all over n. So that's the value I need to plug in my function to find the heights of each rectangle times the delta x to get me an area for each rectangle, add them all together to approximate the area. All right, well, so my function 4 minus this value all squared times delta x. I have found my Riemann sum. So if I was just asked to find a Riemann sum, I could stop there. I wouldn't even need to simplify it. But now I do want to simplify it because my end goal is to have a formula just on the variable n, so I can take a limit as the number of rectangles goes to infinity. Four minus 4k squared all over n squared, still times 2 over n, and now I'll distribute. Oh, let's see, 8k squared over n cubed. And now I have a sum where I really think I can start using my summation rules. So I'm going to rewrite the sum we just had as the difference of two sums. And this first sum, I'm adding 8 over n to itself n times. So n times 8 over n, I'll just get 8 using the constant rule of the sum. Minus, I can pull a constant out front. And then I have the sum of the first n squares. And so I can use that special rule for the summation. That's the same as n times n plus 1 times 2n plus 1 all over 6. So here's my formula. If you give me a value for n, I could approximate the area. In fact, if we plugged in n equals 4, we get that right-hand endpoint estimate. Well, the right-hand endpoint estimate for this would be that lower sum. We get 4.25. But what we really want to do is take a limit as n goes to infinity. And again, we could multiply everything out and look at the polynomial here. But what I know for sure is that when I take n times 2 and I get a 2n cubed, times 8 would be 16n cubed. On the bottom I have 6n cubed. Again, it's a rational function with the same degree on the top and the bottom. So I know its limit as n goes to infinity is going to the quotient of the two leading coefficients, 16 over 6. The limit as n approaches infinity of 8 is just, well, that's 8. And so I have 8 minus 8 over 3 is 16 thirds, is 5 1/3, 5.33333. And so now I know for sure that the actual area of this function that we started looking at in our very first video is really 5.333, repeating forever. With n equals 4, that midpoint approximation was doing a really good job, and I do see that my true area is between that lower sum and that upper sum. But better than that, we finally found the true area under that curve.